Hello, everyone, and welcome back to the Kaspa Miniseries. I'm Alex. We are continuing our mission to compress the epic 7.5-hour The Bitcoin Takeover podcast into small, powerful highlight episodes.
And I'm Jamie. So far, we've covered the why, the who, and the philosophy behind Kaspa. But today, we're strapping in and hitting the gas pedal. We're going to talk about the one thing everyone in crypto is obsessed with: scalability.
This is the big one. How can a proof-of-work system built on Bitcoin's principles claim to handle thousands of transactions per second? Today's episode is called Scalability in the BlockDAG, and we're going to break down exactly how Kaspa's structure is designed to overcome the bottlenecks that limit traditional blockchains.
This was a central theme in Yonatan Sampolinski's interview with Vlad. To understand Kaspa's solution, we have to first understand Bitcoin's problem. Why can't you just speed up Bitcoin?
It all goes back to Bitcoin's 10-minute block time. As Yonatan mentioned, his entire academic journey into this field started with a simple question: what happens when you increase the block rate of Bitcoin? Because it was very apparent that the 10-minute rule was chosen for good reasons.
And the main reason is to prevent something called orphan blocks. Think of the Bitcoin blockchain as a single-lane road. Only one car, a block, can pass a certain point at a time. If two cars try to squeeze through at the same time, one makes it, and the other is forced off the road. It becomes an orphan.
That orphaned car represents a real miner who did real work and spent real energy, but their block was just unlucky. It got discarded, and all that work was wasted. If you try to speed up Bitcoin, say to 1 block per second, you get traffic jams and cars flying off the road constantly. More speed equals more orphans, which means less security.
This is the fundamental scaling problem Kaspa was designed to solve. And its solution is to get rid of the single-lane road entirely. Instead of a blockchain, Kaspa uses a BlockDAG.
We touched on this in a previous episode, but let's make it crystal clear. If a blockchain is a single-file line, what's a block to DAG?
Yonatan described it perfectly. You envision many miners creating blocks in parallel, very fast. Then you get this messy, supposedly messy, graph of blocks. Instead of having one parent, a block and a DAG can point to multiple parents. So when two miners find a block at the same time, the next miner can just say, "I see both of you," and link to both.
So no block is ever an orphan. Every single block that is mined, no matter when, gets woven into the fabric of the DAG.
Exactly, and this is the absolute core of Kaspa's scalability. All that work that was previously wasted now contributes to the network's security. In the interview, Yonatan stressed that this is a pure, a true, a clean generalization of Nakamoto. There's no second-rate citizens. It's just like, take all blocks and try to order them.
No block left behind. So you get this massive throughput because you can have blocks being created in parallel. It's like opening up dozens of checkout lanes at the supermarket instead of forcing everyone into one line.
That's a great analogy. And this parallel processing is what allows for Kaspa's high block rate. But how high can it go? This led to a discussion of the theoretical limits. Yonatan explained that the number of blocks being processed in parallel, what he calls the DAG width, is determined by a simple formula: block rate multiplied by network latency.
So the faster you produce blocks and the longer it takes for them to travel around the world, the wider your DAG becomes, the more parallel blocks you have at any one time.
Precisely. But this creates its own bottleneck. He was very candid about the fact that even Kaspa has limits. The current code starts to struggle around 30 to 40 blocks per second. The reason is what he called quadratic complexity.
That sounds complicated.
It is, but the idea is simple. In the current design, every new block has to reference all the previous block tips it sees. So if there are 10 new blocks and 10 tips, that's 100 connections the network has to process. He explained, this causes the DAG to have quadratic complexity and is one reason why you hit a bottleneck. The very thing that allows it to scale, parallelism, also creates a data overload problem at extreme speeds.
So how does Kaspa plan to get past that bottleneck to reach its goal of 100 blocks per second? Is there a trade-off?
There is. And it's a classic engineering trade-off between simplicity and performance. Yonatan explained that to get to 100 blocks per second and beyond, you have to give up on the simplicity of the mining role. Instead of a miner pointing to all the blocks they see, they would use a probabilistic rule to point to just a subset of them.
So you're reducing the amount of data each block carries to keep the network from getting bogged down, while still providing enough information for the consensus protocol to work.
Exactly. It's an optimization that allows for a much higher throughput. And the benefit of this extreme scalability isn't just about bragging rights. Yonatan pointed out a really cool implication. He said at 100 blocks per second, if you have 1% hash rate, you can mine 1 block per second.
Wow, so even relatively small miners could reliably mine their own blocks very frequently. What does that enable?
It lowers the barrier for applications or large users to participate directly in mining. He gave an example. Imagine you're running a ZK rollup on Kaspa that produces very large proofs. Instead of constantly competing in the fee market to get your data on-chain, you could just mine your own blocks and guarantee your own block space. It creates a new level of sovereignty for users of the network.
That's fascinating. So the scalability isn't just about more transactions per second, it's about changing the very dynamics of how users and miners interact with the network.
To sum it all up, Bitcoin's scalability is limited by its single-chain design, which creates orphan blocks and wasted work when you try to speed it up.
Kaspa's BlockDAG solves this by allowing blocks to be created in parallel and weaving them all together, ensuring no work is wasted and all miners contribute to security.
This parallel structure allows for massive throughput, but it hits its own computational bottlenecks at very high speeds, requiring clever engineering trade-offs to scale even further. The end goal is a system so fast that it changes the fundamental relationship between users and the network.
A truly different approach to the scalability problem. That's our look at how the BlockDAG works. Join us for our next episode where we'll explore DAGnight, the next-generation protocol designed to make Kaspa even faster and more resilient than ever before.
Thanks for tuning in to the Kaspa Miniseries.